Storyline 2 on fuels. We're on lesson 6. Why might the breaking and making of bonds lead to temperature changes? All right, so you should pick up your notes and you need something to write with. So, how are you feeling on this Thor scale before we get started? Today, what you're going to be doing is actively participating in this play pause it. You're going to be working silently and get it done. If you finish, that's a learning. What did we do in the last class? Well, in lesson 5, we experimented with magnetic marbles so that we could model breaking and forming bonds. What do you remember? So what did we figure out? We figured out that breaking bonds appears to require energy in, and making bonds seems to result in energy out, based on what we saw with speed changes. Okay, when we first open the simulation, it's going to look like this. In order to see the parts, I'm going to need to click Setup. Okay, now I can see marble B, marble C, marble 1, and marble 2. Okay, it says strength of 2, and you can notice all of these purple arrows around 2. The strength of 2 is currently at 6. Now, when I move this and change it to 3, it looks like nothing happens. That's because I need to go back up here and click Setup, and now you can notice what changes. If I bring it back down to 0, looks like nothing happened, but go back to Setup, and now I can see the changes. Okay, so it was at 6, Setup, there's the changes. Okay. If you would like to investigate the simulation on your own, which I highly encourage, you can click this link. But where are you going to find it? You're going to have to go into the lesson 6 folder and then right here, open up this page, and that is where you'll find the link. Okay, what are the various pieces of this simulation? Well, particle B and 1 and 2 represent magnetic marbles. How do I know? Well, first of all, I can change the strength. You could say it says magnet 2 and magnet 1, but then I can change the strength. And remember, if I make this also be 6 and click Setup, you can see that I can make there be a magnetic field around both 1 and 2. Okay, how do I know B is magnetic and C is not? Well, let's just go back here, click Setup so it starts like it initially does, and press Go. And when you do that, you can see that B is being pulled toward magnet 2, and then C was just kind of hanging out there. Let's show it a little bit better. Let's move C right here. Okay, click Setup and click Go. I'll pause it now. If I click Go, you can see that if C were magnetic, it would be being attracted to magnet 2, which it was not. Okay. In order to introduce A, I need to do this, which means I'm going to need to bring it in from the outside and click Setup. And you could see here was A coming in from the side, which is just like C, another glass marble. However, I can do this and put a thin metal shell on A, click Setup, and watch what happens. In this case, you can see that thin metal shell, that gray, just like B. So A continues to go forward, and eventually when it gets into that magnetic field, okay, we'll start to get pulled toward that magnet in number 2. And you can see in this graph over here how its speed was increasing. Okay. What about if I have C have a thin metal shell? Okay. So you can see it was starting to be attracted, but let's get rid of A for this one and click Setup. And you could see how both B and C are being pulled, but obviously B is full magnetic, C just has a thin metal shell, so it was less attracted. So those are all the parts. So let's just click Setup again, and pause it. So B was a magnet, right? 1 and 2 can be magnets, but C and A that comes in from the outside are both glass marbles, unless we put the thin metal shell, in which case it then would be attracted to a magnetic field. okay? And B representing as it moves closer, a bond forming between the magnets, and then when bonds are breaking, the particles are knocked away. As you watch this next section of the video, complete this part of your notes. Don't forget to color code your graphs. Okay, I'm getting ready to show elastic collisions, which is showing the perfect energy transfer. First of all, I'm going to remove the magnetic field. Next, I'm going to move B over a little bit, just so that I'm able to see what's actually happening. And then I'm going to introduce particle A, and I'm going to have particle A move in at a speed of 2. So down here, you can see there is a speed graph for A, B, and C. And I'm going to watch what happens as A comes in, and then what happens to the speed of B, what happens to the speed of C and A. So let's start it. You can see A come in, okay? And A came in at a speed of 2 and then hit particle B and dropped down. So now it's no longer moving. All of that energy transferred to B, which started moving at 2. So what do you think happens when I continue this and let B hit C? Well, the same thing. B was at 2, and then all of a sudden it began moving at 0, and C was at 0 and then began moving at 2. So what happened is A hit B. All of the kinetic, remember the motion, transferred to B, an elastic collision. And then B hit C, and all of the kinetic energy was transferred to C in an elastic collision. So this just modeling perfect elastic collisions where all of the kinetic energy gets transferred from particle to particle to particle in a collision. Okay, now I'm going to show an inelastic collision. So here was our perfect elastic collisions where all kinetic energy goes bam, transferred, bam, transferred. None is lost, right? Here we can introduce track friction, and we're just going to bring it to 1%. Okay, click setup. Okay? And then when I click go, I want you to watch what happens this time. Okay, here comes particle A. Oh, goodness. Well, that was different. A started up at 2, but it started to slow down, right? And then when B, it was slow. Okay, so something is happening here. Some of that kinetic energy is being lost or transferred. So friction is causing some of that. Now, we are going to, in our model, just focus on elastic, meaning perfect, ideal collisions. And because in reality, our particles are not rolling across a table with friction, okay? So for our purposes, we are going to focus on elastic collisions and ignore friction, okay? You should have completed this section of your notes. Now check your work as we go over it. Remember, you should have color-coded your graphs, otherwise it's a lot less meaningful. So all kinetic energy is transferred in an elastic collision. Elastic, think perfect. All kinetic energy, bam, transferred. The total amount of kinetic energy remains the same. There is no loss of kinetic energy. It just gets transferred. So graphically, it was represented like this. A had it all, transferred to B. B had it all, transferred to C. C had it all. Okay. Now, what happens in an inelastic collision? Well, some kinetic energy is transferred, but the total kinetic energy decreases. There is a loss of kinetic energy. So what happens is A transfers some of it to B, but some, I don't know, goes somewhere else, it's lost. And then B transfers some to C, but then some gets lost. Okay. Now, for our purposes, remember, we're considering only elastic collisions, only the perfect kind. Okay. But in reality, there may be something inelastic. But for modeling purposes, let's focus on elastic. Remember that bond breaking and bond making involve the transfer of energy. So if I'm talking about the same bond, when I break it, I have to put energy in. And when I make it or form the bond, energy gets released. And so if I form a bond between hydrogen and oxygen, I need this amount of energy is released. If I then break the bond between hydrogen and oxygen, the same amount of energy would be needed or had to be put in. Okay? So when a bond forms, atoms are attracted to each other. They're pulled together by their attractive forces. Okay, what I'm going to do is focus on what happens to the kinetic energy of a particle as a bond is forming. So I'm going to look at particle B and the bond forming with the magnet number 2. Okay, so what I'm going to do is just kind of move C out of the way, just because I don't really particularly care in this case about C. I'm focusing on the kinetic energy of B as it is approaching magnet 2 for a bond. Okay, so let us press go and watch what is happening to that kinetic energy. I'm going to try and pause it right as that bond would be forming. So as B is approaching bond formation, that kinetic energy is increasing. Okay, so bond formation with different strengths of attraction. What happens to the kinetic energy? So look at these graphs. You can see there's one where we have a magnetic strength of 6. That was the first one we started with. Then we increased the strength to 8. What happens to the kinetic energy? And then we decreased the strength to 4. What happens to that kinetic energy? So as bonds are formed, and you can see right here, you have some notes to fill out, the kinetic energy of the system increases, right? Look at the graph. That means higher kinetic energy, higher temperature. Temperature increases. And this seems to be then an exothermic process. Okay? When a bond breaks, energy has to be added in. The atoms are still attracted to each other. So if we don't do anything, they may find each other and form those bonds again. Okay, but when a bond breaks, we have to add energy in. All right, now let's investigate what happens when a bond breaks. Again, I'm not so concerned about C, so I'm going to move it over. What I want to do is form a bond between B and 1, so then I can see what happens as that bond is broken. So you can see my magnet is right here. So what I'm going to want to do is bring B right on top of it. Okay, and I'm going to trade this off. I'm going to make the magnet here be 6 and this be nothing. So let's click Setup. That looks like what I want. I want a bond right now between 1 and B. And then I need to try to break the bond. So I'm going to need to bring in A, and I'm going to just use, again, the speed of 2. I'm going to send A in to break this bond. And we're going to see what happens to the kinetic energy as we do that. Okay, so click Setup and make sure everything is set, and then go. Okay, so you can see what happened as A came in, right? And then what happens as that bond is broken, okay? So what do you see happening? Okay, so bond breaking with different strengths of attraction. What happens to the kinetic energy here, okay? So here is the magnetic strength of 6. That's what we started with. So look what happens to the kinetic energy. And then we increased the magnetic strength to 8 and then decreased the magnetic strength to 4. What do you see happening to the kinetic energy? Okay, so as bonds are broken, and again, you should be filling this out in your notes, the kinetic energy of the system decreases. That means lower kinetic energy means lower temperature. The temperature decreases. This seems then to be endothermic. So with stronger bonds, we see bigger changes in kinetic energy. So particles slow down more when stronger bonds break. Particles speed up more when stronger bonds form. So when are bonds actually stronger and weaker? Maybe this could help us explain why some reactions have bigger changes in temperature or kinetic energy. Remember, we watched the demonstration with barium hydroxide and ammonium chloride, and then we did one with baking soda and citric acid, and we saw temperature changes, but not the same amount. So in reactions that are happening, we have bonds breaking, but also bonds forming. So to break bonds, we have energy coming in, and when we form bonds, we have energy coming out. So how do you think we could use this simulation to show bonds breaking and forming? Okay, so we showed bonds breaking in this one spot, then we showed bonds forming. But how can we show both happening? Well, we could have the magnetic fields on 1 and 2 turned on. And then we could try to break the bond between B and 1 as the reactants, and then form a bond between B and 2 as the products. So what do you think will happen in this case when we run the simulation this way? So what did you learn today? Do you think we are closer to understanding why hydrogen releases so much energy? What do you think?